today's seminar that is going to be delivered by Jaques. Sam is a PhD student in Oxford University. He's researching the cause of quantum attacks on different kinds of cryptography. He has published work analyzing the complexity of quantum attacks on elliptic curves, isogenies, AES, lightweight block ciphers. I can add that in 2019, he submitted a paper in crypto and that won the Best Paper Award in that conference. So we are very pleased to have Sam today. He will present the landscape of quantum computing today. So Sam, the floor is yours. Thank you very much for accepting our invitation.
Thanks. Thanks for having me. Screen should be shared. So I'm Sam, and this is a talk kind of on my view currently, somewhat opinionated on where quantum computing is today and where it needs to go to get to a point where, as cryptographers, we'll start to really care about it. Kind of what started this whole thing was actually this chart I made for Twitter, and it kind of went viral. And by viral, I mean the extra web traffic to my website cost me almost $2 Canadian to host all that. But this is sort of a complicated chart, and what I want to do in this talk is go through it step by step and explain in a bit more detail and kind of expand a bit on some of the points in here. And also, this talk actually is a little shorter than it needs to be. So if you want to interrupt me at any point with questions, that would be great, because I'd rather spend more time early and explain things well, and then that'll also sort of fluff out the time of the talk. So quantum computers in general, they have these sort of fantastic promises for what we'll be able to do with them when we build them big enough and well enough. We can factor in polynomial time. Any search problem we want, we get a quadratic speed up. And for certain chemical problems, we have this unprecedented accuracy that we should be able to get. So this is kind of why people are interested and why we want quantum computers. What are they? Sort of the components that matter for us is that this basic unit is a qubit. And this is really just like a bit that you would think about in a classical computer, maybe a piece of your hard drive that has some magnetization, and it holds a quantum state. And this is sort of like the state in a classical bit. It can be 0 or 1, which we represent with this ket notation. But it can also be complex linear combinations of these two, and this is where all the magic happens. So you can have something that's both a 0 and a 1, sort of half and half, or this other thing, which is kind of something hard to imagine what this is or what it's used for, but quantum computers can do it. We can take any sort of two-level quantum system and we can make a qubit. So some common examples would be superconducting qubits. So you have some superconducting wire, you have sort of current flowing in one direction or the other. This is a lot of the IBM and Google use superconducting. And here's a picture of Google's computer. And this is a quantum computer, but really what you're seeing in this picture is a massive refrigerator. The chip, the actual qubits are kind of, I'm not even sure you can see them in this picture. Mostly what you're seeing is a fridge. The other fun thing about this picture is behind it, you see the huge server rack of classical computers, which are necessary to make the whole thing run. So that schedules all the laser pulses and everything that needs to happen to actually run this tiny little chip of qubits. You can also have trapped ions. These are another popular choice. And so here's a picture, and at this resolution, you can't really see, but you can actually kind of see the ion in the trap here. And basically where the excitation of this ion stores your quantum state. And maybe this is something you've seen in an intro chemistry course, is that you can have the electrons orbiting the atom in different states. And you can also have photonic qubits. So whether the photon is in one position or the other is the qubit. And so it can be sort of in this superposition. And you get experiments that look like this, where you have a big pile of different things that will direct the light around and reflect it or half reflect it. But these are just sort of examples. But really, we can almost imagine lots of different things. It could be qubits. Once we have qubits, then we can store quantum data. Then we need to operate on quantum data. And to do this, we use gates. So a gate would really be anything which changes the quantum state. So for example, flipping a 0 to a 1 or more exotic things. You've probably seen a quantum circuit diagram that looks something like this. And it looks like a classical circuit diagram where you have different wires, and these represent qubits. So in a classical diagram, the wires would represent a bit. And then the little annotations like the H or this thing here represent gates. One difference with classical circuits that I think I want to emphasize is that formally these diagrams represent time going from left to right. So the earliest point is here to the left, and then you first apply this gate, then you apply this gate, and so on. And this is how classical circuit diagrams are formally defined. But really, we can think about the dimension in a classical diagram as space, because if these are literal wires, and we're sending a signal representing the bit through them, then it will propagate through space as it propagates through time, and it will go through these gates one at a time if we print this diagram onto a piece of silicon or something. There isn't really an analogous process for almost all the quantum technologies. So for example, with the superconducting qubits, your superconductor just stays where it is. The qubit is always in that one place. And if you want to perform a gate on it, you would shoot a laser at the qubit. So you wouldn't, push that qubit through a gate. The gate is something that you do to it. So it's a process and not a device. So kind of in that picture, if you remember, there's no quantum gate you can point to and say, that's a gate. That's something that happens when you turn it on and try to run things. So kind of to think, if you later hear, this algorithm requires several billion gates, don't think you need a billion components, just you need to do something a billion times. And kind of another main feature of quantum computers that is very relevant is noise. So this would be any process which modifies the quantum state that we don't really have control over. And this is something we deal with classically also, but usually it's easier to deal with. So if you have, say, your magnetic hard drive and it absorbs a little bit of energy, it's probably not going to totally flip the bit and cause a problem. But with qubit types, this will cause a problem. It will, if your quantum state shifts just a little bit, that's an error. The other thing that makes it a bit harder, I'll answer a question in a second. Qubits can also bit flip, just like classical bits, but they also have a phase flip. And this is something that has no classical analog. And then any linear combination of these two types of errors is also another type of error. So there's sort of an infinitely larger family of possible errors that could happen to a quantum state than to a classical state. So someone says in the chat, does the circuit size simply translate to more time-consuming process in the quantum world? Yeah, basically. So the other thing you have to keep track of is sort of some circuits require a certain number of qubits. And so if your circuit is wider, we'd call it, then that also is, okay, you need this many qubits, right? And if you don't have that many qubits, you can't run it. And then depending on how you often think kind of in a parallel way. So if I have 100 qubits, probably I could do one gate on each qubit separately in parallel if I needed to. So you can kind of think when you're designing a quantum circuit, if you have a billion gates to do, can you squish them down so that you're doing as many of them at the same time as possible? And then the time would shrink proportionally. So the short answer is yeah, circuit size roughly corresponds to time, but there's a couple extra factors. Given the discussion on noise, we can ask, where are quantum computers today? And so here's just a sampling, an incomplete sampling of today's devices, plotted by number of qubits and the error rate. And the error rate, I'm kind of compressing a lot of data here, because quantum computers can have lots of different kinds of errors. So if I have a qubit, trapped ion is sort of excited, there's some probability that it just stops being excited for its own, just for no reason. But then there's also the fact that if I try to apply a gate, maybe my gate isn't exactly what I thought it was, and so we would call this an error. Errors in 2-qubit gates, it's the same principle, but they're often much more severe. Measurement itself can cause an error, so if I try to measure what the quantum state is, maybe this gives the wrong answer. Often these are measured in fidelity, where 1 is perfect and 0 is useless, and so I just took 1 minus fidelity to give some error rate. And then out of all the possible types of errors, I just took the largest. So this isn't really like anyone working in quantum computing would not use a metric like this. This is really just for illustrative purposes. And for example, the Google chip is much lower than the IBM chip, which seems bad for Google, but that's just because Google gave, I think this was their measurement error rate, and IBM didn't print that in their paper. So I'm not actually sure that Google is doing worse than IBM. It's just they gave more data, and so by my own made-up methodology, I had to put them lower in this chart. So I don't want you to look at this and say this is exactly where everything is. This is really more of a rough sense of where quantum computers are today. So given this, we can kind of ask, well, how far are we from Shor's algorithm, for example? So this is, I think, 65 qubits. And maybe you've looked at papers that say, well, it needs a few thousand qubits. But we're not quite there yet. So this is the circuit for Shor's algorithm. And there's three main components. The first is this part which makes a superposition. The last is this part which does what's called a quantum Fourier transform and measures. And the middle part here is the actual difficult part. But really all it is modular exponentiation. So within superposition, you're just basically doing one RSA encryption, for example, or one RSA decryption. So kind of, I like to say that with a quantum computer, it's as easy to use RSA as it is to break RSA, because the bulk of the cost is really in this exponentiation. And it requires, by our best estimates, about 2.6 billion gates. And again, this is something that seems sort of preposterous. Like this is something we think is very fast classically to do an RSA decryption. But if you actually tried to think, well, it's, you know, it's a 2000-bit number, so you need about 2000 multiplications to do the exponentiation, and about 2000 additions per multiplication at least, and maybe 2000 gates per addition. And each of those has some constant overhead. So overall, classically, it's just that our classical computers are really, really good and really, really fast, that we kind of just forget how many gates actually have to go into something like RSA decryption. But for a quantum computer, we actually have to think, oh, 2.6 billion gates, that's a really big deal. And this sort of means that if we have an error rate of sort of 1%, we totally lose out by the time we hit 2.6 billion gates. We need an error rate roughly on the order of 1 over 2.6 billion to get through this without having a big error. So we go back to our chart, and here's quantum computers today. Over here is Shor's algorithm. So we need our error rate to be like 10 to the minus 9, and we need a few thousand qubits. We're just spectacularly far away. So I mean, even if we're doubling the number of qubits every couple of years, like with Moore's law, you know, let's say we get to here in 5 years, we're still nowhere near Shor, because we need to be also getting the error rate exponentially growing, and exponentially growing quite far. This is like 7 orders of magnitude. So kind of what I want to talk about is how are we possibly going to bridge this gap? Someone asked how many qubits needed to reach our promise, which is basically the subject of this talk. So that will be answered as I proceed. Basically, what we don't expect, I don't think anyone expects us to actually get here. And instead, we kind of take a different route, and we use error correcting codes. The idea here is that it's just like a classical error correcting code. Like if you remember your Hamming codes that go into ECC RAM or something. You take a lot of qubits and you connect them together in such a way that they act like one qubit. And what you would call the physical qubits are like the qubits of today, maybe a single trapped ion or a single superconducting qubit. And then the logical qubit is just an abstraction which represents all of those physical qubits working together to hold a single quantum state. The reason we think about error correcting codes is we think, well, if we made our qubits 10 times better than today, it's probably much easier to build 1,000 of them than it would be to try to build one qubit that's 1 billion times better than the qubits of today. So kind of we're expecting that, to go back, moving up on this chart is probably a lot more difficult than moving to the right on this chart. So we'd rather just get to here and then build lots and lots of qubits. And I'll actually talk a bit about the details of these error correcting codes. The main thing that people are thinking about now is called surface codes. And there's lots of reasons these are sort of the dominant approach to quantum error correction. The basic thing is you have this flat lattice of qubits. So in this picture, the white dots and the black dots are actual qubits, and the colored parts represent interactions between those qubits. And the idea is that once you have them, you're performing this error correction cycle where you're performing some quantum gates and you're measuring to detect what kinds of errors have happened. So there's some good and bad about surface codes. The great part about surface codes is they only use this two-dimensional grid and a very low connectivity. So if you look, each qubit only has to interact with its 4 nearest neighbors. And this will be fairly simple to build, and in fact already matches most of the quantum technologies we have today. Google's chip fits this. I think IBM is very similar. So this is kind of why surface codes are the main player. There are quantum low density parity check codes like LDPC quantum codes that have much better rates, but people aren't really sure about them, especially me. I'm not really sure about them because they require arbitrarily long range interactions between qubits. Surface codes are pretty good at suppressing errors. So they're suppressed exponentially based on this distance, and the distance is the width of these little squares. So a single logical qubit is some square patch, and the distance kind of tells you how many errors it can suppress. And so the number of extra qubits, because if this is one logical qubit, then the number of physical qubits kind of is inflated by 49 in this case. The number that you need in overhead is going to be proportional to the square of the log of sort of the number of operations you need to do, because that's how low the error rate needs to be. So basically it's the square of the log of something. So that's not that bad. The problem with surface codes, and the thing that's going to make them really hard, we're going to have to repeatedly measure and entangle half the qubits to actually maintain the state. So this is this error correction cycle that actually makes the error correction happen. And it's this circuit, which is pretty simple, but you're thinking that we'll have to do this maybe 1,000, maybe 1,000,000 times per second to maintain the state of the quantum computer. So this is a lot of operation just to stop the thing from decohering. Just to make a quantum computer work, you need to do all of this. And then once you measure the results, you actually have to solve a classical problem, this minimum weight perfect matching. So kind of it's a perfect matching, you want to choose the minimum weights you can. It's this graph problem that can be solved, but it's going to be a lot of computational overhead to do this for every error correction cycle to correct all these errors. So remember the picture of Google's computer with the big server rack. The big server rack is really never going away. And at some point, we'll probably need to have it installed in the quantum computer to solve these problems as we're correcting errors. And this is kind of not good or bad, just a fact about these things. It can only suppress errors if the physical qubit error rate is below some threshold. Classically, the same thing kind of holds, but the threshold is 50%. I mean, if a bit has more than a 50% chance of flipping, I mean, that's sort of the maximum error you could get. But in this case, the error we need for the code to actually start working is around 1%. And this threshold is also not exactly 1%. It depends on the actual architecture. So if you have, say, your measurement errors are much more likely than 2-qubit gate errors, then your threshold will change a bit, and you also need to change a little bit of the parameters of your code. And here's sort of a diagram kind of showing, there's sort of this crossover point that we find by simulations, in this case, the threshold. So we can put surface codes on this chart, and it looks like this. And I do this sort of fuzzy because we don't know where the threshold is going to be. It's going to depend on the architecture. So it might be sort of by the time we get to here, almost certainly surface codes will work. In here, it still sort of is up in the air. And what's cool about this is we're so very close to this. We don't need many qubits to make one surface code. And the error rate is very close to where we are today. And so people have started trying to implement them. So here's a work from last year, distance 3 code, 17 qubits. Here's this little diagram here. And so the physical qubits last 38 microseconds, but the logical qubit formed out of them lasts 16. You might notice that 16 is less than 38, which seems pretty bad. It should last longer if you do error correction, but the problem is they're not at the threshold. So the error correction actually makes the whole thing worse at this point. They need to be made better for this to work. So I still think this is a really cool result. And it shows sort of a proof of concept of a lot of aspects of the error correction, but we're still sort of not quite there. So we can think about Shor's algorithm at the logical level in a surface code. And so if we're going to do this, we can reach the necessary error rates, but the qubit count is going to grow to the millions because we need about 1,000 physical qubits for every logical qubit. And to give just a sense of the scale, this is a kind of a schematic of an addition circuit in the surface code. So it looks 3D because time is the vertical axis. So it's sort of showing what you're doing to each qubit at each point in time, and kind of each of these dots, I think, is one physical qubit. So this should give you a sense of the scale of this thing. And so we can put Shor's algorithm on our chart now with error correction, and we get these lines. So they're nearly vertical because the error correction scales fairly well. Around the threshold, the qubit counts grow to infinity. But basically, we need something like 20 million qubits to do something interesting, to start breaking our cryptography. And another interesting thing about this chart, there's not a big gap between breaking RSA 1024 and this last one, which I think is RSA 15,000. So, once the early RSA breaks, then at the last one, it's fairly fast to the last RSA. A question jumps in: the fidelity versus qubits. This is the fidelity of the logical or of the physical qubits. So kind of since we need a fixed error rate in the logical qubits to make RSA 1024 work, then basically as the error rate decreases, we need a little bit less error correction. So we need slightly fewer qubits, but it's kind of, we need a fixed rate of logical error to finish Shor's algorithm. So looking at this, my question is, what can quantum computers do in this gap? How are we going to get from here to here? How are we going to motivate people to work on them and build them and fund them? So I'll kind of highlight another issue that kind of makes this gap even harder to cross. I'm not actually sure if you can see because of this thing. So quantum computers aren't doing anything that classical computers can't in principle do. It's just for a classical computer to do what a quantum computer can do, it might need exponential resources. So today we can simulate perfectly about 45 qubits. And if we wanted to simulate 46, you would need twice as much memory or twice as much time. So it's kind of, this is a pretty hard limit on how many qubits we can simulate. And it kind of means that any algorithm, any quantum algorithm you want to run that could run with fewer than 45 qubits is sort of trivial because we can run it classically. Now today's quantum chips, we pass a threshold where we cannot simulate the chip. So the actual physical qubits are beyond what we can simulate. But what about the logical qubits? So to illustrate my point here, imagine we have a quantum computer that is at this point A. So it has 10,000 qubits and the errors are 10 to the minus 3. So it's 10 times better than any quantum computer we have today and has 100 times as many qubits. This seems like an amazing quantum computer, right? But obviously we can't classically simulate this thing. But if we wanted to run some sort of quantum circuit on it, and we wanted the circuit to have more than 31 gates deep, then we need to do some error correction. And when we add the error correction, all of a sudden our 10,000 qubits becomes a lot less because we have to connect a bunch of them just to do the error correction. And we actually only get 44 logical qubits if we want to do any circuit this deep. And 44 is classically simulatable. So we have this quantum computer that's so amazing compared to what we have today, but anything we would want to do with error correction is something that we could do today classically. So we can add sort of a whole region on the chart, which represents points where we have enough qubits to start doing error correction, but once we take off that overhead and think about how many logical qubits we have, it's actually not enough to do anything interesting. And this is even just the logical qubits that could be classically simulated. It doesn't mean that, say, at this point, just past this region, that the quantum computer could do anything more than a classical computer can do. for basically any real world problem, the best classical algorithm is not to simulate a quantum computer, it's to do something intended for classical computers. So I feel like the actual region in which you could start tackling interesting things with error correction is going to be significantly past this. Someone says physical qubits are not simulatable on a classical computer, then how can we program qubits nowadays? I'm not exactly sure what the question is, but I'll try to answer. We can simulate a certain number of physical qubits, but not too many. So we can program a simulator for that many qubits. And the other aspect of sort of programming qubits is there's a lot of work to kind of to make the qubit work. So kind of, you know, a single qubit is this physical device, and often they have little imperfections in manufacturing. There's also a lot of work to kind of tune your device to work for those qubits, which is maybe what the question was answering or was asking about. I hope that answers it, but ask a follow-up if it wasn't clear. So I guess the question I kind of left off on was, how far do we have to go before we have something where the error correction will start to be useful? Like an error-corrected quantum computer will start to be able to do some useful task. So the one idea is probably chemical modeling. This is one of the other big applications of quantum computers. The reason we think they can model chemicals is that at the atomic level, reality is quantum. So like a molecule has a bunch of superpositions of electrons. So it's much easier to model those with a quantum computer, which just naturally handles superpositions, than to try to do it classically. Or so the claim goes. So where are those algorithms? Kind of one of the easiest, sort of the first example people think of is modeling FeMoCo. So this is a molecule that rhizobium bacteria, which are found in the roots of legumes like beans, peas, and they turn atmospheric nitrogen into ammonia. People care about this because even though we can chemically do this process, it takes a lot of energy, way more energy than the bacteria are using. So we figure if we can kind of unlock how they do it, maybe we can do it more efficiently ourselves industrially. And maybe quantum computers could discover some property of this molecule that could help. And I can't really, you know, my own politics says I have to jump in and say, well, this actually doesn't solve a lot of our problems with farming. Like if the farming practice is unsustainable, it doesn't matter. We have nitrogen runoff from the fertilizer. It doesn't matter if we make the fertilizer more efficient. But this is certainly a problem you could maybe tackle with a quantum computer. And it goes here on this chart. So this is a pretty, like one of the earliest, we're not simulating a huge protein, we're just simulating this one molecule, and it goes here. Sort of there's this rapid transition from almost we can't do anything useful with error correction to all RSA is broken. So to me, I'm sort of a little bit worried about, is there any error corrected algorithm that fits in this region that would actually do something useful? And, you know, I haven't seen anything that people have shown will work yet. But the question is, can we do anything else sooner, right? So maybe there's something we can do without doing a full error correction. So maybe we don't need logical qubits, where we can find some application where if the quantum computer goes a little bit off from where it's supposed to be, that's fine, and it still does something useful. One of the big approaches here is called variational quantum algorithms. And the idea here is, you know, there's lots of things you could do with this idea, but a big application is finding the lowest energy state of some quantum system. So for this, typically, it's fairly easy to write down what you would call a Hamiltonian that describes the energy of some system. So maybe you've got some molecule that you care about, and then you have this sort of what is a cost function that tells you what is the energy of this configuration of electrons. And often this is quite difficult to evaluate classically, but it's, again, the quantum computer can handle it naturally. So usually evaluating this cost is actually not that many gates on the quantum computer. And so the idea is, if we had a quantum state, it's fairly easy to measure the energy of that state, if that state represents some configuration of electrons. And so the question is, how do we come up with some state to decide how to measure that? We actually just kind of throw random gates at it. So these theta 1 and theta 2 are just, you you shoot a laser at this qubit for some amount of time theta. And how long should you fire the laser for? You optimize that with this classical thing. So basically what's happening is you use these parameters to construct some sort of trial state, and that gives you the cost, which represents some physically relevant property, like the energy level of some system. And this whole thing is just a black box that some classical optimizer is trying to optimize over. So you're using your quantum computer to evaluate some difficult to evaluate physical function, and then you're optimizing it classically. The nice thing about this is this circuit can be fairly short. It can use not that many gates. A lot of the computational work is being done in the optimizer, and you're kind of just bringing the quantum computer in for one part of the task that is hard for the classical computer. And because you're averaging to find this cost, if there's an error in one run or a couple of runs, it doesn't really matter. Hopefully this all disappears in the averaging. So this is this proposed thing. So then our question is, how many gates will we need to solve relevant problems with variational algorithms? And sort of we have no idea. I'm being a little bit harsh on the vast number of people who do vast amounts of good work on this area. But the basic problem is this is a heuristic algorithm, right? We can't really say that the actual landscape of cost is exponentially large and difficult to reason about. The behavior of the optimizer also hard to think about. So a lot of the work does these small scale simulations, but we don't really have good guarantees that they will scale up well. Lots of times heuristic algorithms work really well, so this could be a very promising approach, and it could be that when we get bigger quantum computers, they will work quite well, but also it might not be. The best I could find for showing actually this will definitely work with this many gates and this much error and solve these particular chemistry problems is this region here. So the error actually has to get down pretty far from where we are today to start being useful in this case. Now, this isn't to say that this is a hard and fast line. This is the area that I have the least expertise, so the most likely that I've simply missed something in the literature. And also an area where there could be easily improvement, and could be just, if we get to this region and we try one of these algorithms, maybe it works much better than we had expected. But I will make some somewhat irresponsible speculation at this point. If these green sections really highlight the first point where things get useful, then there may be no use for quantum computers before any of these green sections. And that's a big gap we'd have to cross. And if there's no use for quantum computing, then there might be no funding. Certainly governments would probably fund it for research purposes, but it's expensive to build and run a quantum computer. Big corporations might kind of give up on it. And so if your livelihood is based on quantum computing today, you kind of don't want people to think that there's a big dead zone. You kind of want to push for actually there will be useful applications. So I think this is why I find it a bit difficult, and it seems to be a bit difficult to sort out at this point what's real and what's hype, because there's a big incentive for the people who are experts in this area to hype it up, because otherwise the whole field dies. And that's not to say there are plenty of people who are in the field and whose livelihood does depend on this and outright say it's going to be a long time before there are profitable applications. But this is also kind of this is why it's a tricky field to reason about. This was sort of the full chart as I had posted it. So I want to extend a little bit and talk about some things that I didn't feel I could put on this without crowding the chart too much. One might ask about elliptic curve cryptography, because it's also broken by quantum computers, and it's a little bit before RSA. So it's slightly easier for a quantum computer to break elliptic curve than it is to break RSA, basically because the bit length is smaller. But again, they're all fairly clustered. So it's, not that much bigger of a computer that breaks ECC 512 compared to ECC 256. The other thing we could ask about is attacking AES. So just using Grover search, which has this square root speedup. And if we put AES on the chart, it looks like this. So here's the RSA, here's AES, and it looks pretty weird because it seems to suggest that AES is easier to break than RSA because the lines are closer. But this chart doesn't have runtime on it. So there's kind of a third axis that obviously I can't show, which is how long does the algorithm actually take to run. If your surface code is cycling at 1 megahertz, which is optimistic but reasonable, the RSA 2048 attack takes 8 hours. So I mean, a dedicated attacker like this would be, this is a huge threat, of course, if you're actually trying to use public key crypto. But at this same rate, it takes 25 billion years to break AES 128. So at this many qubits, AES is totally safe. But this is kind of not a good reflection of how an attack on this would actually work, because we're ignoring qubit requirements, and we're also ignoring parallelism. So instead of AES, let's think about DES. So we all know that DES is insecure. It only has a 56-bit key, and this is not a big enough key. And since it's not big enough, we'd expect that a modern processor, 3 gigahertz, should break it pretty quickly. But actually, it would take about 90 years. It takes about 119 cycles for encryption for a processor this fast to break DES. And this seems weird because DES is considered broken. Basically, we wouldn't use one processor. No one who's actually going to attack this key would just take a single processor and say, go. If you used even 90 processors, you finish this in 1 year. If you use 900 processors, you finish it in 1/10 of a year. And actually, an attacker can afford 900 processors. This is not an unreasonable thing to assume that they have. And so thinking about parallelism for these big attacks changes the picture, because now we can ask a question. Quantum computers have this square root speedup, so it's sort of, oh, they can break AES 128 in time less than 2 to the 64. And is this something that a classical computer could not do? Actually, classical computers could do this. You just need more than 2 to the 64 processors. Now, maybe you say that this is absurd, and I would agree, but it could be done, right? So the time is not enough of a measure of how difficult the attack is. We can follow up and ask, well, classically, what's the cost in gates or operations of this highly parallel attack compared to just a sequential one? And it's about the same, right? If you parallelize just a brute force search for an AES key, it's not going to take you an extra number of operations in total. You just spread it out along more processors. And I think this kind of gives us a habit of thinking about classical attacks in this way, where we just count the number of operations and we say, it's a 128-bit key, it has 128 bits of security, and we don't care about the runtime versus the hardware requirements because we can trade them off perfectly against each other as we need. And most attacks have this property, most classical attacks. And so this is what we just think runtime is proportional to cost. And I bring this all up because this is no longer true for Grover's algorithm. To give a quick explanation of how Grover's algorithm parallelizes, if you have p quantum processors, your runtime with one processor is 2 to the n over 2, and with p it goes down to the 2 to n over 2 over the square root of p. So since this is about the proportional to the cost on one processor, the total cost over all the processors, you multiply that by the number of processors times the cost per processor, and you get 2 to the n over 2 times the square root of p. So the more you parallelize, the more it costs. You get it done faster, but you have to do more total operations. And so this chart shows sort of a not very precise description of the runtime versus the operations to break AES 128. The blue line is classical, and more or less it should be the same number of operations. But the Grover search, this is the time for one processor here, and so it's level above that. But if we have to parallelize, the cost starts going up. And eventually, if you wanted it really fast, it would be even more expensive than classical. But the basic idea is it gets more expensive. So when we think about attacking AES, we have to think about how long we actually have to do the attack. What is the time budget of the adversary? And this is relevant because if it will take 100 years to break the key, for most security applications we can think of, that actually doesn't matter. Like for everything I want to do, I'm not really worried if someone breaks into it in 100 years because I'm gone, right? And so we can start to look at a depth limit on AES, and this really changes the picture. So here's a limit of 2 to the 64 sequential logical operations. So not physical operations, these are logical operations. With 3 gigahertz, then this is 200 years. So it's a spectacular amount of time on a very fast processor. And of course, this is if it's 3 gigahertz of logical operations, that's way faster in physical operations on a quantum computer than anyone's really imagining. So this is being very generous in terms of the attack time to the attacker. And still, AES 128 shoots all the way over here where we need about 10 to the 13-ish qubits. AES 192 is way over here. And to give a perspective of how many qubits this is, if you got them down to the size of hydrogen atoms, at this point, they would cover the entire Earth's surface. So, I mean, this is just completely preposterous numbers of qubits that you would need in this amount of time. So I would say, with extreme confidence, AES 192 is post-quantum safe. I would say with high confidence, AES 128 is also post-quantum safe, based on this sort of reasoning. So that basically summarizes what I wanted to say about kind of quantum computing and its prospects here. And then I'll finish off by mentioning some things that I'm kind of would look for what will show the progress of quantum computing in the years to come. And so, and again, this is very heavily opinionated, but I'd be excited for the first logical qubit, better state teleportation, interesting factoring benchmarks, and also implementations of chemistry problems. One by one, we're very close to logical qubits. So here's one. This is from Honeywell, where they used a color code in an ion trap computer. So the color code is very similar to the surface code, but there's some ways in which it's better and some ways in which it's worse. You need more connections between qubits, which makes it more suitable for trapped ions, where you kind of have any ion can interact with any other ion. But it's sort of uncertain to me. At some point, obviously, this has to stop being true. You can't have all the ions interacting together if the thing is like continent-sized. But this is sort of why I wonder how this will scale. And they did manage to reduce the error rates in the physical qubit to the logical qubits, but they were only able to keep it up for one cycle. So one thing to look for in the future that might be exciting is, can they preserve a logical state for many seconds or many minutes? And then also to see surface codes in superconducting qubits. The other thing that I think will be interesting to keep track of is quantum teleportation. So this has a fancy name, but really all it means is you're moving a quantum state from one qubit to another without actually moving the qubits themselves. So this is very similar to if you download a movie over the internet, you've teleported the movie from the server to your computer without them actually having to send you a hard drive containing those bits. Like those bits were transferred without moving the physical hardware of your computer. Same concept with quantum teleportation. And the reason we expect to need this is that if we need 20 million qubits, it would be hard to fit them all in one single fridge. So we expect maybe we have a few fridges and then we teleport quantum states from one fridge to the other. Trapped ions, this is probably very likely necessary. And the method usually is you entangle the qubits in one architecture, like the trapped ions, with photons, and then send the photons from place to place. And in 2019, there was an experiment that had created such entangled pairs with a fidelity of basically 94%, pairs at 182 per second. So I mean, close to a kilohertz data throughput of this quantum teleportation. So as these experiments get better, that will be an interesting milestone. For factoring benchmarks, I saw someone mention, supposedly quantum computers factored 35, which is a 5-digit number, about a decade ago, and haven't really made any factoring progress since. The reason I think it sort of stalled is that that's kind of the limit at which you can cheat. So a lot of the implementations compile Shor's algorithm to this format that's unreasonably compact. So in the worst case, if you have an element modulo n of order 2, this instantly factors it, and you only need sort of one bit flip. And people kind of rightly wrote some snarky papers that were like, well, I can imagine factoring like a 10,000 bit number with a coin flip if I have such a generator pre-computed. So it's sort of cheating to use those kinds of generators. A lot of the other circuits will compile the multiplication circuits specifically for the inputs, which also kind of is unrealistic. And this is very much my own opinion. I feel like this is one of the first papers from 2015 they really implemented something that to me looked like an actual multiplication circuit in a quantum computer, and they factored 15. And then in 2019, they did 21. And so I would argue we haven't, up to a very vague definition of what it means to really implement Shor's algorithm, we still sort of haven't implemented it for 35. And to give a sense of why this is actually quite difficult, if you don't optimize the multiplication circuits, if you use them as we would use them at the scale of, say, 2000-bit numbers, the number of gates is actually huge. So here to factor 35, you need about 18,000 gates, completely beyond today's quantum computers. So you have to do a lot of optimization to factor a number, even like 35. So this is why it's going to, I think there was sort of a plateau on what we could do. Chemistry, it's a very similar story, actually. And so this is a little outside of my own expertise, but I asked some people about this. What can we do? These variational algorithms, what have they been implemented for? So we've implemented them for beryllium hydride. I think this is called, it's not even on the chart, diazine, and just water. And this L represents roughly the number of gates. Again, to do this, they had to really compile the circuit down. And I've actually saw some other criticisms that they were simulating at a level of precision that was chemically useless. So again, this is sort of something to keep watch for. Are we able to get more accuracy with bigger molecules or the same molecules? And that will sort of highlight progress in quantum computing in the years to come. So that's my milestones to look for. This is the chart as it was at the beginning. Thank you for listening, and happy to answer any questions.
Thank you very much, Sam, for this very nice presentation, really enjoyable. So I have there is a quick question here. Several questions, maybe you can read them.
So how do we make the classical computer communicate with the qubits we have in the quantum computer? Is number one. That at a certain level of detail, I have no idea. I mean, the rough sense is, if you have a gate, and which I think for IBM's computer is literally a laser, then you just classically send a signal to the laser, and it says, shoot a pulse at this particular point at this particular time. And this communicates with the qubit in the sense that it applies a gate to it. And I think measurement is the same. But again, the actual physical details, I don't know. I don't know the full physics of this. And then question number two, in simple words, what is a logical qubit and how is it different from a qubit? I guess what I would say is that a logical qubit is sort of like in the surface code, you would have a bunch of physical qubits and you'd have a little square patch of them, and you'd call that a logical qubit. And what you mean is that there's a way to represent the quantum state of all of these qubits so that you kind of lump a lot of them together and call, so maybe there's a state where most of the qubits are 0 and only a few of them are 1, and you call that a logical 0. And so you're taking a lot of different possible physical states of those qubits and saying that they're all the same logical state, and same for the logical 1. And what this means is that if a couple of qubits flip, then you haven't actually changed the logical state, because the logical state is many of these. So I mean, with classical bits, it's a similar story. Like if I have a repetition code where I encode 0 as 3 zeros and a 1 as 3 ones, I could really, then those 3 bits represent one logical bit. And so if one of them flips, then it doesn't cause an error in the logical bit, because I can say, oh, if 2 bits are 1 and 1 is 0, I can just flip the 0 and get back to my state. I hope that sort of explains.
Yes, thank you, Sam. There are several comments. Thank you so much for this overview. I really enjoyed it. Thanks a lot for the great talk. Thanks. So I have a question for you, Sam. Well, 2 questions. What do you think about the D-wave quantum computers? If they can be called quantum computers? Because you
Yeah.
mentioned, yeah.
So they are doing basically a whole different approach to quantum computing that doesn't fit in the kind of qubit and gate model of what a quantum computer is supposed to do. And so they're using quantum systems in a way that they will hopefully do some computation. And every time that I've asked someone about this or looked into it, it seems that the consensus among people who work in quantum computing is sort of quite dismissive, because it seems that everything that their computer can do, which is very specialized problems, there are specialized classical algorithms that work just as well or better. Basically, it doesn't, and like you couldn't run Shor's algorithm on their computer because it doesn't fit in this paradigm. So I'm not super, what would be the word? I don't have a lot of confidence in their computers or their claims for this reason.
Okay, thank you very much. Another question for you, Sam. So we say that classical AES has 128 bits of security. Post-quantum AES would have how many bits of security? Can we have like a number?
Yeah, I mean, that's a tough question, because let's suppose that you define the number of bits of security to be, if you say you have 50 bits of security, it would take 2 to the 50 quantum operations. The problem is the number of quantum operations depends on the depth that you're allowing your attacker to have. So you can no longer just say, oh, it needs 2 to the 50 operations, because that amount could change. You could take the minimum number of operations and you could say, well, an attacker who has, as long as they want to break it, I think for AES 128, it's like 2 to the 76 operations. But then that's probably not realistic, because that's going to take so long, no attacker will ever have enough time to do that. So it just becomes, I'm not sure that bits of security is sort of a great way to describe the security of attacks against Grover, or things that are vulnerable to Grover.
Okay, and my last question, and it's probably the expected question. How many years do you think that we need to wait until we are in the useful zone that is plotted in this slide for quantum computers?
Yeah, it's hard to speculate. I think we can say, I think I once did the numbers that, let's say that we can double the number of qubits every 18 months. I think it's about 30 years before we hit the 20 million mark. And that assumes that as we're doubling, we've also bumped up the error rates to something over here. And I also checked, we haven't been hitting and I say we, the people who actually build these things, haven't been hitting a doubling every 18 months so far. So the rate of qubit count doubling has to increase to hit that, and then we need to maintain it for that many years.
Yeah, we need to wait then. We have one more question from, maybe you want to read it, Sam?
What do you think about D-Wave quantum computers? Yes, I answered mostly, but I'm sort of, they don't seem to be doing anything that we can't do classically, and I don't have much reason to expect that they will. So, yeah, not very confident in them.
Some people has been very harsh on D-Wave, calling it even a fraud. Do you think that this is too harsh? Because at the same time, they have had some nice developments. I think entanglement, experimental entanglement, they say.
Yeah, I mean, I think experimental entanglement is pretty straightforward. Like, you don't need much quantum hardware to do that. And like, I don't want to say, basically, I don't know enough about D-Wave to be confident enough to say my opinions if the talk is recorded. To be totally frank. Yeah. So that's kind of, to say that they're a fraud really then depends on what their claims are, right? And if they say, well, we have this like annealing-based computer that may have advantage in these particular types of problems, that's a pretty defensible statement, but it also doesn't say much.
Okay, fair enough. Okay, so I think that there are no more questions. So thank you once again, Sam, for this wonderful talk, and we really enjoyed it and learned a lot.